Welcome, guys. Um, I welcome you once again to another phase of explanation on Math 312. From our previous video, I was actually trying to contemplate on this example here. So we want to try this question, but let me give the full details. So let's say, okay, let's call this example 3, which says, okay, let me put it this way. Given the function, given the function fn of x equals this same expression that is here. We have it as nxe minus nx squared. So the same range is also given, where x is a member of a closed interval 0 and 1, 0 to 1. So now where n is also 1, 2 to infinity. So full stop, let me just put a full stop there. Let's say there's a full stop there. And then the question now says, what relationship, what relationship exists between the integral of f and integral of fn? That's the first question. What relationship exists between this and this? Let me put a full stop, and also let me ask another question. Is integrability valid or not? When you take the integral of it, this integral that you have here, is integrability valid under the limit operation? Under the limit operation. So let's confirm. So this question here is similar to what we did in example 2. Okay. So this one here is this actually implies integral of f of x dx, and this is integral of f of nx dx. And I believe you know the definition for f of x. Fnx is converges to the limit as when n tends to infinity of fnx converges to f of x. So I believe you know the definition for f of x in that case. So let's just go straight to the point in this case now. So proof. Let's show the proof. So to prove this now, let's start with this. Okay. So now we actually given fnx to be equals to nx e minus n x squared. So the first thing for us to do here now is to evaluate this integral first, and then evaluate this. Then after that, we will now tell the relationship that exists between them. So let me start with this integral that is here. So considering the integral of f, which can be written normally as integral of, we already have our range of x as is a member of 0 goes to 1. So I'll write it as 0 goes to 1 in this case. And my f itself can be written as fx dx. So this is how I want to start. So I'll now write it that, okay, where we believe that, or it is believed that f of x is equals to the limit as when n tends to infinity of fnx, right? This is a definition that we already knew. And then this will be equivalent to limit as when n tends to infinity of fnx is already given to us as nx e minus nx squared. So I believe that since the limit is actually based on n, this x can actually move outside from the integral. So if x move outside from the integral, I'll be left with limit as when n tends to infinity of ne minus nx squared. So looking at this, if I substitute my n for infinity, I'll have infinity, then e raised to the power of minus n infinity square, and that's raised to the power of infinity. And n raised to the power of infinity, that should be equals to 0, I think. Okay. Looking at this, all this expression here, we end up giving us 0. Take note of that. It is very, very clear. Infinity square is infinity times n, that is infinity. So looking at this now, it's as if I'm having infinity times 1 over e raised power of infinity in that case. So if you try to evaluate this out, the result is infinity. Is that clear? The result is infinity. Okay, sorry, it's zero rather. It's zero. The result here is zero in this case. It's zero. It's zero. Okay, so since I have x here, and then every expression here has turned to zero, so if I multiply this, I will end up having zero as our final answer, which shows that fn of x, okay, is pointwise convergence to this. So the pointwise convergence is at fx equals to zero. So it's pointwise convergence in that case. But take note, not all pointwise convergence converges uniformly, because the I think the converse is not true. But I believe that any sequence function that converges, that is continuously, that is that converges uniformly, every sequence that converges uniformly, we always have a pointwise convergence, but the converse is not always true. Please take note of that. Converse is not always true. So since this is equals to zero, that means the fn of x is pointwise convergence to zero, or to f of x, where f of x is equals to zero in that case. So now let's consider this. Since we already have this result now, the only next thing for us to do now is to go ahead and evaluate the second one. But we're looking at this now, you know, we having this kind of expression. I think okay, I think in this case now it's n that is n. Sorry, it's n that is infinity, right? It's n that is infinity. N is infinity here. X is outside. So here in this case now we end up having n over e is to the power of nx. Yeah, n over e is to the power of nx, and then we have infinity over e is to the power of infinity. And if you evaluate that, this thing here implies that you have infinity times e is to the power of this what are infinity, this is n over e is to the power of nx squared. I think this is what we are going to have in that case. And then looking at this now, it's as if you have infinity over e is to the power of infinity. So if you evaluate this take note that the result is zero. Please take note of that. Zero. Okay. So since we already have this to be equals to zero, that means we've gotten an answer for this one. Okay, we've not taken the integral. Okay. So what is integral of f? Because mind you, this result here is for f. My f of x is equals to zero in this case. So the next thing is integral of f of x dx, as when you have zero goes to one. That means we have it as zero goes to one. F of x is already equals to zero. Yes, and that is equals to zero. So this for the first part. And for the second part, whereby we have integral of fn. So let's check. Integral of fn now can be written as 0 goes to 1 of fnx dx. This is normal way of writing it. So then we end up having 0 goes to 1. My fnx now, okay, my fnx now is just this expression that is here, which is n. We are given this as nx, right? Nx e is to the power of minus nx squared. This is what we have as our fnx on the other hand. So this is what we have. But please take note. I noticed that we we will still have to take the limit, outside the integral. Okay. This one here, we still have to take the limit outside the integral according to the way we have it. You have to take the limit outside the integral. This one is limit inside the integral. This one is limit outside the integral. But let's solve this out first. Then we take the limit at the end of the day. So what we still have to do here now is that we still have to take the limit as when n tends to infinity, just like the way we've done it earlier. I think this was the expression that we have, right? Where it goes to one. Okay. So then looking at this now, we need to evaluate this integral. Mind that I still have my limit as when n tends to infinity here. So if I want to integrate this one, I can use a substitution method such that I will let this represent you. Let u represent nx squared. such that du over dx, n is constant in this case now, such that du over dx now with respect to x will now be equals to 2nx dx. 2nx, right? That's 2nx. 2x, the n is constant. So if I make dx the solid of the formula, I should have du over 2nx. Please take note of that. Okay? So if u is equals to nx squared, so what is x in that case? Because, okay, I can still leave x the way it is so that this s can cancel the down part. So I think that's fine enough. So whatever I'm going to have left now is that I still need to consider the range. The range now, when x is 0, u is remain as 0. That's nice. But when x is 1, u remain as n. So I have to explain the range also. State the range. So for the range, when we have x to be a member of 0, comma 1, and if x is equals to 0, what will be our u? U is equals to 0 as well. 0 squared times n, that's 0. But if our x is equals to 1, what's going to be our u? If x is equals to 1, I have 1 squared times n, that's my u is equals to n. So in this case now, I'm having 0 goes to n. When x is 0, I have 0. When x is 1, I have n. So here I have n, then I have x, and I have e to the power of minus this nx squared is already u, and this dx is already du over 2nx, such that x will cancel x, n will cancel n, so I'll be left with just 1 over 2 in that case. So I have limit as when n tends to infinity of um, integral of 0 goes to n of e to the power minus u du. So this is what I have left. So if I take the limit of this guy here, so if I take the limit of, I still have over 2, right? I have 1 over 2. So let the 1 over 2 come outside the integral. So I have 1 over 2 in that case. So I have 1 over 2. If I integrate e to the power of minus u, that should be, with respect to u, that should be 1 over, differentiate minus u. That's minus 1. Then I'll repeat everything back. So this is what I'm expected to have. I believe you're familiar with that. That's how to integrate in that case. So looking at this now, I'm left with limit as when n tends to infinity of 1 over 2, open bracket. Okay, now I'm having negative of e is power of minus u here now, left. And I'll still have to insert the upper limit and the lower limit, right? So I have 1 over 2. When I insert the upper limit, I'll have minus e minus n for the upper limit. When u is n, put substitute one as n, minus when u is equals to 0. Now this for the upper limit, minus the lower limit. I still have a negative sign again, minus 0. And n to the power of 0 is 1. So this is equivalent to limit as when n tends to infinity of 1 over 2 of minus e minus n, then minus, this is 1, minus minus 1, and that should be plus 1 in that case. That should be plus 1 in that case, right? That should be plus 1. Okay, no, this is e is power of 0, 1 over e is power of 0, and that's 1. So minus and minus is plus. I have that in that case. So next thing for us to do from here now is to evaluate that. I have limit as when n tends to infinity of 1 over 2. So then I have 1 minus e raised to the power of minus n. So looking at this, I can decide to take the limit separately. Let's say the 1 over 2 is outside the limit, which is a constant. This 1 over 2 can come outside. So this is what I have left now, 1 minus e minus n. So looking at this, is a very straightforward one to do, times, if you have limit of a plus b or a minus b, it's still equivalent to limit of a separate plus limit of b. That's property of limit. So I can split this thing up. I can have this as limit as when n tends to infinity of 1 minus limit, this minus sign is there, as when n tends to infinity of e to the power minus n. So that's what I have in that case. So then the next thing for us to do from here now is to, when you take the limit of a constant, take note, the result is a constant. That's all. Whether it tends to infinity or not. Okay. The limit of a constant is that constant, 1. then minus. This one I'm having limit as when n tends to infinity of e raised power of this. And I believe that should be 0, which I already explained. This is saying you have e raised power of minus infinity. And e raised power of minus infinity is 1 over e raised power of infinity. So, and this will always give us 0. Please take note. This will always give us 0. So 1 over 2 times 1 minus 0. So I have this final result now as 1 minus 0 is 1 times this, that's half. So which implies that the integral of fn, when you take the limit of this integral of fn, I have it as 1 over 2. So on comparing, let me just recall, let me write it out clearly. Recall, so I have to write it well. Recall that integral of f that was given to us, which is equivalent to something of this nature, integral of the range of 0 goes to 1 of f of x dx. We have this result as 0. Okay, let's call this equation star. And we also have another definition that says fn, which simply implies that we have the limit outside the integral of 0 goes to 1 of fn x dx. This is what this one means. While this one simply means limit inside the integral of fn x. I believe you understand that. So this is 1 over 2. We have this result as 1 over 2. And let's call this equation star star. So now that they ask us, the question says that we should state the relationship that exists between them. That means they are not equal. That's the relationship that exists between them. So on comparing, I'll just give it a final conclusion by saying on comparing the two, on comparing star and star star, okay, we conclude, or we can actually conclude, let's say we conclude that the relationship that exists between them, we conclude that the relationship, let me write it this way, the relationship that exists between them is that what? And I will write it out clearly. The integral of 0 goes to 1 of limit as when n tends to infinity of fn x dx is not equal to, very easy, just like what I've explained earlier. Okay, 0 goes to, I think this one is now when the limit is outside. Okay, this one is actually when the limit is now outside. They are not equal to each other. Okay, now I'm having 0 goes to n in this case. I think that was what I had for that case. Then I have f of n x. Yes, the range for this one is 0 goes to n. But if I initially 0 goes to 1, let me use that. But initially it was in terms of x. So on comparing equation star and star star, we conclude that the relationship that exists between them is that the limit inside and outside the integral are not equal to each other. So I think they also has another question. They also said, is integrability valid? That means since they are not equal, which implies that they are not valid. Since they are not equal, that means integrability is not valid. Okay. So on comparing this, we conclude that the relationship that is between them is that this is not equal to this. Okay. So I can just say which implies which implies um which implies that the integrability is not valid. Please take note. Is not valid. And it can only be valid unless um fn of x, that sequence function given to us, unless fn of x is uniformly convergent, like I used to say, is uniformly convergent to what? To that f of x equals to 0. Under what range? On that close interval 0 and 1. That's all. This explain the full, you get your full marks straight up. So when I say something is uniformly convergent, there's a way I've not explained that. I think that should be our next topic. I've not really explained that. I've not really touched it. But please take note that since this and this are not equal, okay, that simply implies that the fn of x is not uniformly convergent since they are not equal. That's why. That's why I said unless it can only be valid unless if f of nx if fn of x is uniformly convergent to zero, straight up to zero. When it's uniformly converges, when it's uniformly convergent to zero, that means f of x equals to zero in that case. So is that you just write uniformly convergent to zero or uniformly convergent to f of x, which is equals to zero on that close interval 0 and 1. So I just think that's all we need to explain for that. Let's check again. Is that all the question that they asked that I asked earlier? Is integrity valid? No. Under the limit operation, it is not valid. So it can only be valid if this fnx that is here converges uniformly to zero. So that's just a simple explanation there. So let's take another example, which is example 4. I think we still have enough time to do that. Okay. Let's take example 4. So I have to change the color for this one. I have to change the color. Let me change it to this color here. Because okay. Example 4. Example 4. This example 4 now, we now want to deal with limits. We don't want to deal with integral again. We have been using integral, right? So this in this case now, we don't want to use integral. And then this is our fn now. We don't want to use fn. We now want to use fnm. What if you have fmn rather? M come before n. Like we are now having two terms, like two different sequence, like double sequence. We have sequence m and we also have sequence n combined together. Fmn. No, this is just Fn. Now you're now having Fmn. So in this Fmn, whatever we want to show now is that we want to try to show that when you take the limit, when you take let's say you take n to be fixed. If n is fixed, that means limit as when n tends to infinity is outside, is fixed. So inside the bracket, you will now want to consider m tends to infinity. Okay. In this case, we always say that the one outside is fixed. Okay, we always take n to be fixed, and then you take the limit of m tends to infinity in the bracket. So let me explain that clearly. You see, I will surely take an example for that. So just hold on, let me give you a very clear example. You know, you take n to be fixed outside and m is fixed inside. So what limit are you taking for this m? It's actually when you have f of nm. And this f of nm will be given to you. It will be given to us for sure. It will be given to us. So if you try to evaluate this, and then you now try in this place now, n is fixed. This for fixed n. What if you now have fixed m? If m is now fixed, if m is fixed, that means the limit of m will be outside. M will be outside. Then you are only considering n to be inside of f of nm. So if I now ask you that if you solve this one, taking n outside and when you take m inside, if you solve the two, are they going to be equal? That's my question. Are they equal to each other? Automatically speaking, they cannot be equal to each other. Just like saying if you have integral, okay, but now you are not using integral, you are not using limits, but with double sequence, which is mn in this case. How do we go about this? So let's take an example. So we want to show that these things are not equal, or just consider. I think I have a question that okay, I have a question on this. So example 4, let's say given let fnm, okay. So yeah, why am I writing nm? M come before n, right? So let me correct that. Okay, mn. So this is a double sequence, and then we now have the sequence in it has a combination of m and n together. Let's say we have m over m plus n. Unlike we having just fn equals to, let's say we are now having just n squared x then 1 minus x is power of n. We are only considering just n. We can't call this one nx. So okay, can't call this one nx. X is just a boundary, okay, of 0 and 1 in this case. So in this case now, I think we are not considering any boundary. We are just having just mn, no boundary in this case, where m starts from 1 to infinity, and at the same time n also starts from 1 to infinity. That is, m is first term, n is also first term to infinity, and something like that. So this is what we are given. Now we now want to show that does this satisfy? So now let's check. If you are given a double sequence of this format now, what do you a double sequence function given to us here now? Whatever you have to do now is to take it one after the other. So I have to let for fixed, okay, let me just use this word. Let me just say for fixed n, for fixed, let's take n to be fixed. We will take n to be fixed first. Take n to be fixed. That means if I take n to be fixed, I will now have something of this nature. Limit as when n tends to infinity, okay, outside. Then I'll have to solve the one inside the bracket first. M tends to infinity of fnx, of fmn rather, fmn, this is what I have. And this will be equivalent to n is fixed outside, but I want to consider m first, okay, inside the bracket. That's why I have m inside the bracket. So what is my fmn? My fmn is m over n plus n. So if I ask you to find the limit as when m tends to infinity of this, that means any other letter aside from m is a constant. Okay, so which simply implies that I will have n tends to infinity here outside, and then when you want to find the limit as when m tends to infinity in this case, whatever I have to do now is to divide each of the term by m. Since I'm considering m, I will divide this one by m, I will divide this one too by m, I will divide this n also by m. That's how to find the limit in that case. So if this m cancel this m, I will have 1. Remember that I still have n to be fixed outside the bracket. So I'll be left with what inside the bracket? I'll be left with, if m cancel m, I have 1 over, I still have limit as when m tends to infinity. Let me cancel this. Limit as when m tends to infinity. I have 1 over, and I have 1 plus n over m. So if I now insert my m to be equals to infinity, so what am I going to have? 1 over m tends to infinity, that means I will have 1 plus n over infinity. And since n is a constant, n is a range of 1 goes to infinity, 1, 2 to infinity, then I should have, I once told you that, I think I've also explained that if you have anything over infinity, that should be 0. So this n over infinity is 0. So I have 1 over 1 plus 0, which simply implies that limit as when n tends to infinity, I have 1 over 1. And that is limit as when n tends to infinity of 1, right? Of 1. So limit of a constant is a constant, so the result is 1. So for the left hand side now of this expression I want to prove, when n is, this for when n is fixed, and this for when n is fixed. For so when n is fixed, I have it as limit as when n tends to infinity of 1. The whole of this one is 1. And when I find limit of 1, I have 1. So now let's confirm whether this second one will also give us 1 or not. That's our main target. So that's our main target. So then, my battery is low. Whoa. So for the m part, if you try to take n to be fixed, take m for fixed m, for fixed value m, that means limit of m is outside and limit of n is inside of fmn rather. So when you solve this out, please take note. If you try to do this, when you take m to be fixed, you will end up having this one as 0. This one will give you 0. So when you find the limit as when n tends to infinity of 0, you have 0, which is not always equal. So they are not always equal to each other. So because of I think my battery is low. So let me quickly save this and send this and upload this one for us. So thanks for watching. So please take note, they can never be equal. The first one is 1. This left hand side is 1, while this one is 0. You can try it out. You notice that the two will not give you the same result. So that's how it works. Thanks for watching.